Okay, so we've got to the point where we've defined the card data type. And here's a couple of examples of that. So representing a couple of cards, King of Hearts, Ace of Spades, otherwise known as David and Death, respectively. Now we're getting to the fun bit, because we're going to put all these bits together and represent a hand of cards. Now, in fact, there is already a perfectly good data type to represent a hand of cards, and that is a list. So we could define a type synonym, another name for an existing type, and that type synonym could be written as using the keyword type, and we could say that a hand is just a shorthand way of referring to a list of cards. So that would be one way of representing a hand, and in some ways that's probably the best way of representing a hand. But that's not what we're going to use here, because we're going to learn something about defining our own data types rather than just reusing existing ones. So although that would be a very sensible way of doing it, we're going to do it in a slightly less sensible way by basically defining our own version of lists for lists of cards. And this will be a very useful pedagogical exercise for recursive data types, because not all recursive data types can be represented by lists, just this particular one. Okay, so let's start with a definition and see what we can make of it. So a hand of cards is something which contains, well, it could contain no cards at all, the empty hand, one card, two cards, three cards. So there's any number of cards. All of those things are possible to represent using a list of cards. So how are we going to represent it here? Well, we're going to represent it by making a distinction between the case when we have no cards and the case when we have at least one card. So we're going to represent that as a choice between two different constructors. The empty hand of cards will just be represented by a single constructor, empty. And a non-empty hand of cards we will represent by adding a card to some hand. And that hand may or may not be empty. But if we add a card to a hand, we know we end up with a non-empty hand. So I'm going to use a constructor called add for adding a card to a hand. So this is the shape of our definition. It contains two new constructors, empty and add. And in order to create a hand, we either use empty or we add a given card to a given hand. Now, what do we notice about this definition? What's special about it compared to definitions we've seen so far? It's recursive. The definition of the data type hand is defined using the data type hand. So just like we see recursion in the way we define functions, we can also have recursion in the way we define data. Let's give an example of a hand. An example hand could be the hand obtained by adding the card David to the empty hand. So that is an example of a hand with one card in it. An example with two cards can be obtained by adding another card to a hand with one card in it, namely X1. So there's an example of a hand with two cards. Let me compile that. What happens when I look at, for example, X2? I'm just going to pause for a second for you to think about that. Well, what happens is Haskell doesn't know how to print these things out. So we need to do, as we did before, deriving show. Now you might be tempted to throw in everything you can think of here, deriving show, deriving EQ, for example. But it's not actually obvious that EQ, a derived equality operation, would make sense on hands, because the order of the cards in a hand probably doesn't matter most of the time. And so the derived equality will actually not respect that. It will say that this hand is not equal to this hand, even though they are in fact the same hand. So it's probably not a good idea to derive EQ for hand. Okay, let me reload that file and look at example 2. And as you see, when Haskell, the Haskell interpreter calculates the value of the X2, it replaces the definitions by the things that they are defined to be. So it replaces the David by the David card and the Death by the Death card and so on. And that's the example of the card, the hand with two cards. Now, of course, this is not something that we would actually likely to print out in a game involving hands. This is just our Haskell representation of this data structure. So to see that in action, I think it's good to take an example. And I'm going to take the simplest example I could think of was the size of a hand of cards. it's one of the simplest examples. So we're going to look at the size of a hand of cards. So it's going to be a function from a hand to a size, which is going to represent by an int. So how do we define size? Well, we're going to define it. Since hand is defined as a recursive data type, then it's going to be very natural to define functions over that data type using recursion. And until we've defined a few functions of that kind, then we can't really do anything useful with a recursive data type unless we use recursive functions to define operations over them. So we're going to define the size function by pattern matching according to the two kinds of hands that there are. There's an empty hand and a non-empty hand. So an empty hand, the size of an empty hand, well, that's 0. The size of a non-empty hand, what does a non-empty hand look like? It has a constructor add in it. The add, the arguments to add will be a card and a hand. Notice that this is a constructor. It's going to appear in my code. This, and this are the types, representing the types of the arguments to the add constructor. They will not appear in the code, but they may appear in the types. So what is the size we get from adding a card to a hand? Well, let's suppose we knew what the size of this hand was. Then if we knew that, then we'd know that this hand is 1 bigger. In other words, the answer would be 1 plus whatever the size of this one is. But what is the size of this? Well, it is the size of h. In other words, we use recursion on this smaller hand to calculate the size of this bigger hand. And there's an example of our first recursive function over hands. And if you want to contrast that with the length function over lists, if we had, for example, a length function which takes a list of things and computes an int, it doesn't matter what the things are, we could define that recursively by saying the length of the empty list is 0, and the length of a non-empty list, what is a non-empty list like? It's a thing on the front of a list of things, and that would be 1 plus the length of the rest of the list. So the fact we say that in fact our data type is really like the data type of lists becomes very visible when you see the list version of this function, where the add constructor, the corresponding constructor in lists, is the cons operation, which although it's written as an infix operation, it's essentially the same as the add, it's doing essentially the same job. Okay, let's look at one more example, a slightly more complex example, and that is the hands beats function. When does a hand, I've got a hand of cards, and there's a card on the table, and the question is, can I beat that card? And remember, we're going to use the functions we defined earlier, which was card beats. So we have a hand and we have a card. So let's define this guy, and we're going to use the same recursive pattern on this first argument. So the hands beats functions takes a hand as the first argument and a card as the second. So the first argument can be defined, we're going to define this in two cases. What happens when you have the empty hand of cards and a card to beat? And the other case is what happens when we have a non-empty hand, and that's to add a card to a hand. And note I'm using C and C prime there for the names of the cards in my definition. So this is the card we're trying to beat, and this is the card we have at the top of our hand. So can we beat a given card if we don't have any cards? The answer is no. So the answer there is false. What about the second case? Can we beat this card? Well, it depends. If this card can beat this one, then the answer is true. So if C prime, get my primes right, I'm going to use the card beats function, and I'm going to use it in infix form because it's more easily read. So I think it was called card beats. If C prime card beats C, then the answer is true. Otherwise, we need to check whether the rest of the hand can beat the card. So either it's true either if this is true, or if the rest of the hand can beat the card. In other words, or if the rest of the hand beats the given card. So I'm using infix notation to hopefully make it a little bit more readable. And so you see that we can beat the card given either if this one can beat it or if the rest of the hand can beat it. And that's why we use the or operation, either this or that. So if either one of these is true, then the answer will be true. We just compile that and something's not quite right. Trying to work out what this error is. A bit puzzled, maybe something down. Okay. I'd actually put in a code stub for hand beats just by saying it's undefined. That's a little trick for writing a syntactically correct incomplete definition. So that was the cause of my little problem there. So sorry about that. Do you remember the card David was the King of Hearts and the card Death was the Ace of Spades? So we can ask whether Death. We can ask whether let's what are my examples? EX1, that one. Does that hand beat David? So can that beat the Ace of Spades? And the answer is no. Okay, so the final part of this series of small videos on the hand, we'll look at 3 different ways of splitting a deck into red and black cards, using 3 different styles of recursion. So this will be a very useful overview of the styles of recursive definition. And all of these things will be very useful in the second lab.